Oh, all right. So, what are we going to be talking about today?
We're going to be talking about the ideal gas law. The math that we've been doing before has to do with the combined gas law. We're using pressure, volume, temperature, all that. So those are coming back for this formula. But the only difference with this one is that we don't have an initial and a final. We don't have a P1 and a P2. We just have a P. Same for B1, B2. We just have a V. All that.
Okay.
So this is the formula right here.
So, since we don't have any ones or two, does that mean we're not dealing with changes?
We're not dealing with changes, exactly.
Oh, okay.
We're dealing with things like as is, as they are.
Right. So, like, if you have the volume and the temperature and the amount of gas, then you can solve for figure out how much pressure is on it.
Exactly.
Okay.
Yeah.
Okay.
It's all pretty simple. The other new thing that we have here is the ideal gas constant right there, which we will it will be available to you on a formula sheet, and it looks a little something like this. So you get your STAR chemistry reference sheet, and look, it's right there.
Okay.
And it all depends.
There's three of them.
Yeah, it depends on what units you're using.
Okay.
For pressure. So when you look at your P, you look at the units that come after it, and that will determine which number you use. Like if your pressure is in atmospheres, then this is the ideal gas constant you use.
Okay.
0.0821. If you're using kilopascals, it'll be 8.31.
And if I'm using millimeters of mercury, I'll use 62.4.
Exactly. So you just take a look at your P, the units that come after your P, and then take a look at your reference sheet, and I'll tell you which R you need. And it says right here, R is equal to your ideal gas constant.
So I see there's an equal sign between all of them. Does that mean they all mean the same amount? It's just a different unit?
Yeah, exactly.
Oh, okay. All right, great. Let's take a look at this this formula again.
Right, so we got pressure.
Okay.
And that could be in atmospheres, or that's atmospheres, not ATM, like at your bank, right? Or it could be in kilopascals.
Okay.
Or it could be in millimeters of mercury. Any of those three.
Okay.
Temperature, actually volumes in liters. Right there, we got our moles. We got our ideal gas constant. Temperature should be in Kelvin.
All right.
There you go. Unless it asks you to change it to Celsius, in which case you do your conversion, right?
Okay. Right.
Yeah.
Right.
So let's look at how we use this formula.
Let's look at this. This is written in the packet. We just rewrote it here to make it a little easier.
Yeah.
So, how many moles of oxygen will occupy a volume of 2.5 liters at 1.2 atm and 25.0 degrees Celsius?
All right. See, isn't that so nice? I love not seeing like it was this and changed this, like initial and final and all that.
So I still want to make a list of all these things, right?
Oh yeah, absolutely.
Okay.
So we'll write down our notes like we always do, right?
Okay.
We got N, that's our number of moles, is what we're trying to find. So make a question mark for that.
So how many moles, right?
Yep. We'll occupy a volume, so V of 2.5 liters.
Okay.
Pressure is in 1.20 atmospheres.
Okay.
And the temperature is in 25.0 degrees Celsius.
Okay. Isn't temperature supposed to be in Kelvin?
It is. So now we got to convert it to Kelvin before we can do anything with this, right?
Okay.
What do we do? That's on our formula sheet, actually.
Oh, is it?
Yeah. Look at that.
Okay.
We got it highlighted right here. You might want to highlight it on your formula sheet.
So 0 degrees Celsius is equal to 273. So if I have...
How many do we have?
What do I have? I've got 25. So if I add 273 to it...
That will get your temperature in Kelvin. And what does that come out to?
It would be 298
Kelvin. There we go.
All right.
Now we can use it in our formula.
Okay.
So we just plug everything in right here.
So
we got our formula is PV is nRT.
nRT. Okay. My pressure is, we said it was 1.2.
Yep.
Okay. My volume is 2.5 liters. Okay.
Move this up a little bit.
All right. And that is equal to
N,
which we don't
trying to
have,
find.
so we're going to leave that as N.
Yep.
And then we've got R, which, we
yeah.
didn't write down an R. Which R do we use?
So it said that we're in atmospheres, ATM,
Right.
so that means we're going to use 0.0821.
Okay. All right.
So let's put that here in our list of knowns, because it does count, right?
Yes.
No, 0.821, and then I'll plug it in right here. And then we got a temperature of 298.
Okay.
Now to solve, just got some algebra to do.
Mm-hmm.
I like to solve this part first, and
Right.
then you just rewrite everything once I got it all solved on both sides.
Mm-hmm.
So we're going to have 0.0821 times 298. You're going to punch that into your calculator?
Sure. .0821 times 298 is equal to 24.5 if we round it.
All right.
And then we've got 1.2 times 2.5 is equal to 3.
There you go. Then we just divide both sides by 24.5, and that will get us our number of moles,
which is approximately 0.12.
And moles.
Moles. All right.
There you go.
Okay.
Excellent. And that's pretty much it. So let's try a couple of problems from the guided practice here.
All right.
So these are in your packet right here under your guided practice. There's the one that we solved right there, so we can just skip on down. Oh, and look, they have everything all laid out. Alright, so we want to know what volume will 2.00 moles of nitrogen occupy at 720 millimeters of mercury and 20 degrees Celsius. Okay, so I'm going to write down our knowns. I'll move it down a little bit so you guys can see.
Okay, so we've got 2.00 moles, so that's our N. And we've got 7.20 millimeters of mercury, so that's pressure.
Yep.
We got 20 degrees Celsius, so that's a temperature, but we want that to be in Kelvin.
Yep, so plus 273 makes that 293.
Okay.
Kelvin. And we want to know what our volume is going to be. And what R are we going to use? For milliliters of mercury.
So there's a milliliters of mercury R, isn't there?
Yep. We look at our formula sheet. We're in millimeters of mercury, so that means we're going to use 62.4 as our R. So R is going to be 62.4.
Okay.
Cool. So let's plug everything into our formula.
Right. PV equals nRT.
Yep. P is 720. And our volume is what we're looking for, so we're just going to leave that there as a V. It's kind of a sloppy V, my bad. And we got 2 for our number of moles.
Right.
R, 62.4. And then temperature, 293. Okay, so we're going to solve this part and then divide.
Plug all those into the calculator. 2 times 62.4 times 293 is 36,566.
That's a big number. Which is equal to 720 times V, and then divide by 720.
And we get 50.8.
All right. 50.8, and that is in
liters because it's a volume.
Sweet.
Okay.
Well, that was pretty easy.
All right, I think I'm getting the hang of this.
Yeah.
All right, let's take a look. At what temperature in Celsius will 5.0 grams of chlorine gas exert a pressure of 900 millimeters of mercury at a volume of 750 milliliters.
Ooh, man.
Okay, so we're solving for a temperature. We've got...
Temperature is what we're trying to find.
Right.
And that's in grams. Oh, we need it to be in moles.
Okay.
Man, there's a number of conversions we're going to have to do.
All right.
How do we go from grams to moles again?
We're going to have to set up our train tracks, aren't we? Terrible. Okay, so my 5 grams is my given.
Yep. We told you this stuff would come back, guys. That means grams of chlorine is going to have to go on the bottom there. Oh, this is chlorine gas, though, so it's going to be Cl2, isn't it? So Cl2... That's what I want to watch out for, and then 1 mole on top. So chlorine is 35, but we got 2 of them, so that's going to be 70. Yeah. So we should do 5 divided by 70.
Okay.
Let's enter your
That'll
calculator.
be my job. 5 divided by 70 is 0.0714.
714 moles. Okay, so we got an N down. And then we got a pressure. Our P is 900 millimeters mercury. So that means our R is going to be, put my R over here, R is going to be 62.4.
Because that's the one that lines up with millimeters of mercury.
And then volume is 750 milliliters, but we want that to be in liters. So we're going to move our decimal place 2, 3 spots to the left, so that makes it 0.75 liters. Okay, so I think we got everything.
Okay, so now let's just plug everything into formula. PV equals nRT.
Our P is 900. Our volume is 0.75. Our N is 0.0714. Or R. Our R is 62.4.
Okay.
Because we were in millimeters of mercury. We found that in the previous problem already. And then temperature is what we were trying to find.
Okay.
So leave that there.
Alright, so the first thing we're going to do is multiply 900 times 0.75, and you get 675 if you do that.
Okay.
And then you also multiply 0.0714 times 6.224. And you get...
Oh, it's 62.4.
0.0714
times 62.4.
2.4.
Yeah, there we go.
Okay, so it's 4.46 if we round.
6.
Yeah.
Alrighty, times T. So then we just divide 675 by 4.46.
And we get 151.
Okay, so that's actually in Kelvin, though.
Oh.
So, and we need it to be in degrees Celsius. Is what they said in the problem.
So whenever we went from Celsius to Kelvin, we added.
Yeah. So
273.
this time,
so we're going to take our 151 and we're going to subtract.
We're going to subtract 273.
3. Okay, so I've got a negative number. Is that right?
That's okay.
Okay.
Negative just means that it's really, really, really cold.
So, well, yeah. Okay, negative 122.
122 degrees Celsius.
All right.
That is extremely cold.
All right.
122 below zero. Man, that was a heck of a lot of conversions.
It was.
But none of them are really difficult. It's just a little time consuming, right? Just take it one step at a time.
Okay.